Welcome back to another episode. Today we're going to be talking about pre-embedded systems. Basically what you should know before you even touch a circuit. So if you happen to be one of these software developers and you happen to grab, let's say, a fuzz board because it makes it really easy for you to connect things and you're programming it using a familiar Visual Studio, .NET, C#, whatnot. But then you've never worked with embedded systems before or you never worked with circuits, it's pretty scary to wire even an LED. For us who've been doing it for a while, it becomes natural. We forget how much information we know. So I try to summarize as much as I can of like the pure basics, the stuff that you really need to know. Now, first of all, you need to understand what is a voltage. Now, a voltage, you can think of it as a level of energy that is carried on by electrons going into a circuit. So for example, in the US, the power is 110 volts. Your car battery is most likely 12 volts. A small circuit runs at 5 volts, and now newer circuits to take things into more lower energy and lower the cost on processors or microcontrollers, they are 3.3 volts. There are even lower voltages. We don't want to get into that today. But the most common today for a circuit is 3.3 volts. Let's leave it at that. Now, why the different voltages? Well, just because it's different needs. We cannot put 100 volts in everything. First, if there's 100, let's say there is 100 volts running through the circuit and you touch it, you're gonna get electrocuted. You probably die. So now going down to lower voltages, something like 10, 12 volts, that's what you have in your car, 12 volts. That is decent, but then the current needed to run the circuit at that voltage is higher than what is desired in today's technology. That's why 5 volt, it was the norm, let's say 10, 20 years ago. Now it's 3.3 volts any way you look typically on microcontrollers. What is current? Current, if you picture electrons as people, and each one of these, the charge is a bag of charge. Let's say I'm like one of the electrons and I have a bag of charge on my shoulder, and that's how much charge I have. The higher the voltage, the larger the bag. Now, electrons is how many of us going through a road. So there, let's say the wire is a road. So the wider the road, the more electrons can go by. That doesn't mean there are electrons going by, but that is the limits. So I may be just me on a highway walking across or through the highway. That's just the one electron. So there isn't that much current going across, but the highway is so wide that allows for a lot more electrons to go across. Power going through your home is an alternating current, it's AC. That means the direction of electrons is going back and forth, and this has a very important reason. Let's not get into that. But then DC current is always going in one direction. That's how batteries work, for example. Like the battery and the AA battery in your remote or the battery on your phone. In a typical embedded system, because that's DC, it's running off a battery. Now, to get voltage to your circuit, to connect this to, let's say, power it off like you want to plug it into an outlet, you would need a transformer. What that transformer does is reduce that voltage. You take the 110, 220, whatever that voltage is, you drop it down to the voltage you need to run the circuit. And let's say it's 5 volts or 12 volts, whatever that voltage might be. And it also has a small circuit inside that converts that alternating current to direct current. And another option could be USB. The voltage coming out of USB port on your PC is 5 volts. And it has enough current. Remember the current, the voltage, we talked about those? It has enough current to run a small circuit, charge your phone. It's made for accessories, basically. Or you can also, another option is get one of those power banks, which basically is a battery that you plug into your PC and it gets charged up, and then from there you can plug it into a circuit and it's reversed the role. Instead of charging it, you're using it to run your circuit. because of the direction, there's the plus side and the minus side. So if you look at your battery, for example, let me show you this over here. I didn't bring a battery. So let's say this is a battery. There's like a little notch up here. So this will be the plus side, and over here will be the minus side. So when you wire up things, they need to be wired up properly. So over here, it shows that the plus side is the inner pin going into the circuit, and the outer is the negative side. This is very, very common. But if you happen to get a power pack, you have to make sure that the outer shell is the negative and the inner is the positive, so we don't have a reverse voltage. Now we have added protection circuit on our design. If you happen to plug in a transformer that has a reverse voltage, it's not going to damage it. But it's not going to work, of course. So once that voltage gets into the microcontroller and the microcontroller is running, now there are pins coming out of the microcontroller, and that's what you control in your software. And those pins can be high or low. That's what we call them. High meaning it has a voltage on it. Low meaning it's same level as the negative side, the zero side. So that's the ground, negative. Sometimes it's just GND, short for ground. That would be the minus side on the battery going into the circuit, and that would be the reference for our voltage, right? Now, from the microcontroller, from these pins, each pin can be either at 0 volts in reference to that ground or negative. So we call it ground because that's like the ground level of what we are talking about when it comes to voltage levels. Or the pin can be high. High in this case is 3.3 volts because the microcontroller is running at 3.3 volts. So when you set a pin high in your code, that pin goes up to 3.3 volts. You set it to low, it goes to 0. It doesn't go below 0. What can we do with these pins?